Okay, so this is a video on electromagnets and motors, and I want to begin by thinking about what is an electromagnet. And you saw something like this when we talked about solenoids, and you did a lab about solenoids a few weeks ago. And we're going to be talking more about this now. But imagine you have a coil of wire like this. That's what you're going to make in lab. So this is wire. And imagine that you could put a current through this wire, and you could do that, of course, by hooking it up to a battery like this, and the current is going to flow through the battery around these coils of wire, and then it's going to come out like that. But the fact that the current runs through these coils like this makes it kind of like a solenoid. And what we'll see in class is whenever you have a current passing through a wire, you generate what we call a magnetic field. When the coil of wire is in a circle like this, the magnetic field results in there being basically a magnet associated with this coil of wire. From a side view, if I could look at the coil of wire like this, from the side, on the top of it, you'd have one pole, the north pole, let's say, and on the other side, you'd have the south pole of the magnet. So it's as if you had a little magnet inside the coil of wire that looked something like this. A bar magnet, which is one type of magnet you'll see, where the north is on one side and the south is on the other. The orientation of the north and south depends upon the direction of the current. So if it's clockwise, it'll go one way. If it's counterclockwise, the other way. We'll talk more about that in class. The important thing is that this coil of wire generates a magnet, north and south. So I'm going to go to a new slide here. If you have this coil of wire here, imagine again, and underneath it you have a magnet like this, where one side is north, the other side is south. And let's just say that the current is passing through this coil such that the magnet that's created inside the coil, I'll draw it in red, has its north right here and its south right there. Now the question is, what's this coil going to want to do? And you know that if there's two like poles here, the north and north, they're going to repel each other. So this coil, if it could move freely, you'd say, well, it's going to go that way. But what's actually happening is the coil is going to be kind of trapped, so it can't move up, but it can rotate. So these wires here are kind of like the bearings that hold the coil up, and they will allow it to rotate so that this north is going to move either that way or that way, but it's going to rotate. It's going to try to get away from the other north. All right? So you're going to get a little bit of motion going on here as a result of this interaction between the magnet and the coil of wire. So how does it become a spin, which is what we want the motor to do? We don't want it if it just repels for a while, it'll stay there, which is okay, but we want it to spin. We want it to keep moving. So how can we make that happen? So we're actually almost there. I'm going to show you. I'm going to go to another slide here. And in this slide, I will again draw the coil of wire. And what I'm going to say here, this coil actually has to be insulated. That means it's coated with a small layer of something so that you actually have separate turns of wire in here. If they're not coated with something, then it's like you have one loop here. You want to have many loops. So the wire has to be insulated or coated with something in order for that to happen. Now imagine then that you sand or get rid of some of the insulation on both sides of this wire. On this side, you're going to get rid of the insulation both above and below the wire, all around the wire basically. Yet on this side, you're only going to get rid of the insulation on one side of the wire, like that. Okay, so imagine that, and then imagine that this wire here is resting in a loop. So I'm going to draw a loop here that's basically supporting each end of the wire. But it's a conductive loop that's tied to a battery. Okay, so this loop here is tied to that battery, plus, minus. And you also have a magnet right below here. Now imagine this. Imagine you get that little North Pole here in this coil of wire like that. There's that North Pole that's created when the system hooks up. That North Pole causes this coil of wire to rotate. When the coil of wire rotates, the part of it that was connected here, because it was in contact with the wire, is no longer going to be connected. It's going to rotate away and not be connected. So while this side over here will still be connected, this side over here on the right will not be. So as the coil rotates, as it turns here, this side is going to break its connection, and you're not going to get any current flowing through the coil. So when it starts rotating, it'll keep rotating because it has some inertia. It wants to keep moving unless there's something to stop it. So there's nothing to stop it. There's no north or south anymore that would stop it. So as it rotates, it keeps rotating until it passes around again. It passes around to the side again, and it reconnects on this side. And so you get a current flowing through the wire again, in which case the North Pole again repels from the North Pole of the magnet, and the same thing happens. And what you get is you get the coil of wire to be spinning, perpetual spinning motion. Many different designs for this type of device were developed, particularly in the 1830s, by a whole number of different people. After the breakthrough in 1820, when we realized that magnetic fields are created by electrical currents, shortly thereafter, people began to realize that you can cause things to move, and they were trying with all their might in the 1830s, a number of different people, to create motors that could actually perform useful work from electrical currents running through them. And this is exactly what you're going to be making today or on Monday in lab. Okay, good luck with that.